Okay, now let's get started. First, I like to talk about some student they asked me a question regarding this decision table. So, well, let me maybe repeat that a little bit. So, in the decision table, we have this. Okay, well, this several parts. All right. First, we have in the left corner, left up corner, we have all these conditions specified. Like here, if you still remember this question regarding this example regarding the flight, when the cocktail will be served, and what is the price of the cocktail, and where should the cocktail be served? Is domestic or international? Okay, so that's actually specified here. All right. So for these conditions, first up left corner we have all these conditions. First, we extracted from the description of the requirements description. First condition is if it's domestic or not. Then it is if it's over half or not. Then the price is over 350 or not. Okay, that's three conditions. That's clear, right? Three conditions. And then we have the rules. We specify the rules associated with the condition. Because the condition, they have the value, right? Like domestic has a value y. That means, what is a y value in the domestic? That means it is domestic. That means that yes, it's a domestic. Okay, and the n value means not domestic, international. Okay, that's only two sort of flight. Alright, and over half four also have this two value y and n. Over 350 y and n. The purpose in the rules, like how many rules are there, the purpose of that is to calculate how many different combinations are there. Okay, so if all of them has a two different variables, so it's going to be 2 times 2 times 2. All right. Well, say if here if it's include domestic, international, or you can someday travel to the space, well, okay, then the domestic, this condition has 3 values. It becomes 3 times 2 times 2. Right, those 3 times 2 times 2, 24. No, 3 times 2, yeah, it's 12 possibilities. Right, but here, since every condition has only 2 values, it's 8. Okay, it's 2 times 2 times 2, 8. Alright, so that's the rules and conditions. Rules associated with conditions. And it's a y, 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 and y, y. It's different combinations there, alright? Also, what's even more important, we have actions there. Why we specifying these rules? Because we have a different combination of the conditions, then we need to react it differently with different conditions, right? For example, here we want to say if it's domestic over half 4 and over 350, then we will serve the cocktail there, but it's not free. We need to specify this as an actions, right? And then but if it's domestic and over half, but if it's over half for over 350, but it's not domestic, it's international, okay? Then we serve cocktails for free. We serve cocktails, yes, and it's free, yes. Okay, so we need to specify conditions, actions, and also the rules and the associate. When we specify the rules, we first specify the combinations of the conditions. Then we specify the action for that combination. Right? So we need to have condition and actions. Okay, so that's it. Yeah, and we pick up from here. We were talking about the state diagram, right?
My question is in a tree, when we create the tree, action is going to be in the last tree. It is a
Yeah.
decision table.
Yes.
But in decision
Oh, tree. Yeah.
So action, it has to be there, or we just need the condition. We are just doing the condition and rules.
Yeah. Let me show you. We need, well, in every situation we need the action, because if you're making the decision, that means you are taking the action. So we need action to be there. See, here is where you specify the action. The last part, the end node. Yeah, that's where you specify cocktail free, that's the action. Serve cocktail for free, that's the action, right? So, well, decision table, decision tree, there are some tools that help you to make decision. What is make decision? It's taking actions, reacting to some conditions, right? Alright, let's talk a little bit more about the transition diagram, or state transition diagram. Well, okay, so this state diagrams, like I mentioned last time, we use that to specify the change, the dynamic behavior of the system. Okay, because system, it react to different, different maybe control, different situation. The system is in different state, right? So we use state diagram to demonstrate the behavior of an object. Okay, every object will have its state. So anyone here know what is a state of a, okay, let's start from here. Object. All of you know what is object, do you? Or not? Class and object. Okay, we know what is class, what is object. Okay, so what is object? Maybe it looks like. So what is object? Yes, an instance of the class. All right. So what is a class looks like? Well, let's just say class. See, this is a class. All right, I'm just finding some code here so that I won't use the whiteboard. It will help the online student to see these things. Okay, so this is a class. First, for a class, we have a class name, right? And what are these? Yeah, the variables. What is the attributes, or sometimes we call the member of that class. Okay, and then we have a lot of functions to maybe manipulate something in, for manipulate the value of this members, something like that, right? So okay, or reacting to different value of the member. Okay, so when we say object, it's some instance there of this class. All right, so what is the state of an object? Here we say there, state diagram demonstrates the behavior of an object through many cases of the system. Okay, we use state diagram to describe the behavior of the object. So that means an object will have different states, right? So what is an object's state? How do we define the state of an object? when we change from a state to another, let's assume, okay, the light, it has two states, right? Two states, right? It's on and off, right? Two states, right? Let's assume the light, this light here, is a class, or this light, this particular light, is an object of the light class. Okay, it has two states, on and off. Okay, so do you think on and off, what do you think? That's, well, if we abstract this light into a class, the on and off, what are those in the class? Is that variable or operation? Method? Any different opinions? State. Yes, a state. On and off is state. We call state. But how do we define on and off? Okay, so here, on and off, they're actually the value. There are two values, on and off. It can be Boolean, or sometimes you can use 0, 1. It depends on how you define it. But it's a value of some variables of the light class. Okay, I can imagine if we define the light class, it will have at least a variable that shows whether it's on or not. Like a Boolean variable on equals to false or equals to true. Okay, something like this. Okay, so it's a class light. Right. So we will have maybe Boolean value of on and off. Right. Maybe we have another value called its color of the light. Right. Color light color. Or it could be something like this, and it will also have some functions like void, okay, turn on. And we do something here, blah blah blah, to turn it on, and void turn off. Right, that looks like a class of light, right? You see it clear? It's clear? Okay. So this light have a different state. Maybe so while the on and off is actually a value of this variable, right? Boolean on. So if this on, well, I can here actually turn on means on to true. Well, if we turn off, okay. So on and off, there are two states of the light, and on and off, there are also a value of this Boolean, right? Of this Boolean. So therefore, remember this: the state of the object, it depends on the value of the variable, of its member. Okay, depends on value of this member. So here we have a different method to change. We have turn on and turn off, different kind of methods to change the states of the light. The method, we use them to change the state, to switch from one state to another. But, well, if we say, okay, there are two states there, on and off, what makes the two state difference? It's a value of its member. Okay, so that's how we define the state of an object, the behavior of an object. Right? Okay. So sometimes the behavior of the object is changed quite dynamically. That's when we want to use this state transition diagram. Okay. And how to draw a state diagram? So it's something like this. We have a state name. For example, we just have on and the light, right? State name, we can say it's a light here. It's a light. And during its state, what it's doing is just it's on and it's illuminate this classroom. So that's the activity there. Yeah. And also we have a transition here. Means the change from one state to another. So we need to specify the condition there in order to change from one state to another. Okay. Okay, here's the example. So this is the initial state, which is the dummy node. Okay, just tell you when this state, all these things start, where should I start it? Okay, so it's from initial to state 1, and from state 1 it has two possibilities here. One is, well, condition 1 happen, you go to some condition happen, you go to state 3, and then some condition happen, you can go to state 2. But can we change from state 3 to state 2 in this diagram? Yes or no? No. Why?
It's either on or off.
Yeah, because this is no way. There's no connection between these two states, and there's no condition specified. You can do nothing to connect these two states. All right, and you don't even have a state coming from state 2 to coming back from state 3 to state 1. If we have a connection from state 3 to state 1 with the condition specified, okay, then we actually find a way from state 3 to state 2, but through state 1. Alright. But if we have something connect state 3 to state 2 directly, that's actually, well, that means we can switch from state 3 directly to state 2 when some of the condition is satisfied. Okay, so here look for an order object. When the object enters the checking state, it performs activity check items. After the activity is completed, the object transitions to the next state based on the conditions. Okay, let's say here from start dummy node, from this start, we first go to this checking state. So here what we are doing is we are trying to check the orders. All right, we're checking, well, like you're making the order in the online store. First they are checking, okay, if you have all the items available in the store. Okay, so when you're at this state, if all items are available, it will transfer to the dispatching state, and what this do is initialize the delivery, and then from dispatching to delivery there's no condition specified because it's automatically transferred from one to another when that is finished, when dispatching is finished, and that makes sense here, right? Okay, but from the checking to cancel, we need to meet the condition that an item is not, at least an item is not available. Then we cancel this order. But can we do from dispatching to cancel in this diagram? No, there's no pass, right? Not such a pass there. So if you want to go to the cancel stuff thing, like dispatching to cancel, probably there's no way. Well, it's gonna be delivered. Maybe there's nothing for return, but not in this process. Yeah, and sometimes you can group some of the state together, like a layer, right? Like you encapsulate this two state into one bigger state. Then you have a in and out to and from this big state. So it's kind of like a group. You can do that as well. Yeah. State. Try to see if I can find any exercises here. Okay, I like to have some small exercises. So let's take out a piece of paper and trying to draw a state transition diagram for, let's say, for a washing machine. Okay, washing machine. Let's try that. All right, 5 minutes. Okay. First, we start from a dummy node, like a start point. Let's think back about how you do the washing process. Just make your own assumption. I know some of the washing machine has fancy functionality, but make your own assumption about your washing machine. I'll just include maybe as much as you can in 5 minutes. I'm gonna need a volunteer who can share your answer on the blackboard. Oh, whiteboard. Okay, it's blackboard. A blackboard. Any volunteer? Yes. Thank you. Okay, so for online student, you can, well, if you're watching this video afterward, you can skip this maybe 5 minutes waiting time. Thank you, but is any conditions there, or it's just automatically go there?
I didn't need to pay for it. I just pay when it's ready.
Yeah. Thank you. Okay, thanks. Alright, so let's maybe start from here. Let's see what we can do. Good. So usually, first thing here is the initial state. That's nice. And actually, it's not in the slides, but in state transition diagram, we have another type of domino. It's called the end. It's similar to the start. It's just called end. So we can just maybe, if it's ending, we can make it go from here to here, right? So what the condition you put is since the water, all the water is gone, it's dry, right? So sometimes, yeah, that's a good condition, maybe with sense. Okay, so well, the washing machine is pretty like automatically running from, well, it's kind of linear process from one to another, right? It's not very complicated. But if but here it's good. We have a state. We have the kind of the same as state name, but it's the action of the state. Well, in this case, it's But here is actually we should say it's dry. So we just go to the end. And here. From here, the state, we can have this type of state, or the self loop. So here, like when we have when we have the sensor, after the spin session, we find that it's not dry, it's still wet. The clothes is still wet. We can start another spin session. Okay, something like that. Okay. And let me see if I can find something that connects things back to wash.
Some of them said it's like the amount of soap.
Okay.
That could be a condition.
Yeah, let's see. Actually, from here, from rings to spin, it's not always like from rings to spin. Sometimes
Yeah,
you
the
can
water.
choose to go back to wash for another time. Well, it depends on the setting, right? So, yeah, time is down, time up. When time is up, you go from the wash to the rinse. And then from the rinse to spin, rinse to wash, it may, well, let's think about this way. For this circle, wash, rinse, wash, rinse, it may repeat 3 times. Let's assume we only go here when the 3 count. It's up. When it's more than 3 times, right? Okay, so here the condition is the count greater than 3. Okay. So here the count. Counter is less than or equal to 3. It go back to wash. And here, if the counter is greater than 3, it goes to the spin. And spin has a sensor. So if it's still wet, it goes to another spin. If it's dry, it goes to the end. So this actually is not a linear process, which makes actually the washing machine a little bit smarter, more intelligent than this linear go from wash, rinse, and spin, right? So that's how we. But if you want to say, okay, this thing is more intelligent, okay, so it can handle different situations dynamically, then probably using this state diagram, state transition diagram to model it is a good choice, good option. I'm gonna take a picture of it and upload it online. All right. So that's state transition diagram. Any questions regarding this? It's pretty simple, right? Just state the action, the transition between, right? Okay, it's nice. Let's talk about UML. So, well, now it's the second half of the semester. We're going to actually do a project. We're going to actually modeling a system. So we need some of the tools to help us. This UML is one of them. Okay, first let's talk about the visual modeling. All right. So when we're doing the modeling, a lot of ways to model things. First is we use some. Oh, turn this on. Sorry. Visual modeling. Okay. So what is modeling? Modeling is the thing that captures the essential parts of the system. Different ways to model. We can use mathematical language. We can use we describe the system, right? Or even the state transition diagram. Do you think that's a model? That is a model, right? Well, that's the essential part of the system of the washing machine. Given this diagram, you know how this washing machine works, and it's pretty straightforward. Alright, so visual modeling is modeling using standard graphic notations, like the state transition diagram. Okay, so we all have everything predefined. We all have this boxes defined as state, and the lines as transition. And beyond the line, I tell you this is the condition of doing that transition. So if we do not have a predefined standard graphic notations, okay, I will define this conditions on the line, but maybe you want to define the condition somewhere else, so that makes things worse. So that's why we have this standard notations. Like everyone will stick to these notations so that we all understand each other, like we're speaking a language, right? So it helps us to build things, mapping things from business domain to our domain that we create a project for them. And I'm just going to quickly go through this. Yeah, and visual modeling promotes reuse because, so if that system behaviors are well defined, so that this knowledge, instead of just a whole bunch of code there, we know the structure of the system from the visual modeling, then this kind of knowledge can be passed on maybe to another system, another developer can understand more about the system. It promotes this reuse of the existing system, because we know the scope. From the visual modeling, we know the scope. It's clearly to tell the scope of the system and functionality of the system. Okay, so it promotes the reuse. So what is UML? UML, the Unified Modeling Language. Do we take any course regarding UML before? Okay, good. So UML, Unified Model Language. There are a whole bunch of UML things. It's a set of standard there. Includes a whole bunch of diagrams. Okay, state diagram, state transition diagram is one of them. We also have a lot of other things. Alright. So it combines the best practice from data modeling, business modeling, object modeling, and component modeling. It helps us to visualize the system, like we tell that system, the behaviors, the definition, the functionality of the system, pretty straightforward. Yeah. So with that, one lot of benefits. Just we describe the boundary of the system, so illustrate the use case of the system, and represent the system with the class diagram, which is directly mapping to the classes we actually using the system, and state transition diagram, which we just did, and the architecture of the system, and extend the functionality of the system. And let's go to this. Use case diagram. Let's see. Okay, when we talk about system, We don't need a whole bunch of theories for use case diagram. We can just look at this example, all right? When we talk about system, the first thing we do developing for the system is to collecting this requirements, right? So use case diagram create to visualize the relationship between the actors and use cases. Most of the time it's in the requirements domain, like it helps us. So for this system, okay, we have different actors. Well, all this persons here, humans be here. We have a student, we have a professor, we have a register using this system, okay? And also, this actor is not actually an actor using. This is a billing system. It says billing system. It's actually an external system, but we treat it as an actor. Okay, so it's not within the current system. So all this, although it's like maintain the curriculum, request the course roster, maintain the schedule, they are the use cases of system, like what you do with the system, and it's associating this use cases with the correct user, like the professor, they request the course roster through the system, and register, they request the maintain curriculum. To do the maintain curriculum use case with the system. And here, the maintain schedule, okay? The student use the system to maintain the schedule. And this system use a billing system. Well, when you maintain the schedule, you remove something in the class, okay, that trigger some change in the external system called the billing system. All right. And we treat the external system as an actor, okay? As long as it's something external to this system, it's an actor. Student is an actor, billing system is an actor, and some other system we're using, and so it could be an actor. So that's a use case diagram. Just it specifies the relationships between actors and these use cases. And then we have in UML we have a sequence diagram. So it displays the object interaction arranged in a time sequence. Okay, so everything is happening in the order of the time. Right? And we have a different object here. So here we will have first we have a registration form. This is one object, and registration manager another object, math 101, math 101 section 1. So here we have 1, 2, 3, 4 objects here. Okay, so this diagram shows how these 4 objects they are interacting with each other when the student is trying to register for a course. Okay, so it's numbered here, so it's pretty straightforward. Here, let's see. First, what the student do is to fill in the info with the registration form object. Okay, and then it submit the registration form. And then the registration form called the add course function from the registration manager, and it passes the parameter of Joe, which is the name of the student, and the course he wanted to enroll. Alright, so it's Joe Math 101. Math 01. No, Math 101 should be, yeah. And then the registration manager, this object, registration manager object, they ask the Math 101 object. So, are you open? Right? You need, when you're trying to register for a class, you need to check is it open or not. So, yeah. And Math 101, what Math 101 did is it check if there's a section open, because a course can have different sections. So it check with the section 1. Okay, are you open? So if they get the answer, yes, yes. Well, maybe there should be a feedback, yes and yes. Then 6 is you 8 Joule. And to Math 101, Math 101, 8 Joule to the section 1 of the Math 101. Okay, so everything happens in order, right? So here you can see the 1, 2, 3, 4, 5, 6, 7. Well, the upper part happens before the lower part, all right, in time order from top to down. Okay, top down. That's the time order. So this is a sequence diagram. It just reflects how every object. So here, every instance, every row is actually every column that's an object there. Yeah, so that's a sequence diagram. When we talk about sequence diagram, we know that actually sometime in a system, it's not like that. An object exists from the start to the end. Sometimes the object be created, sometimes the object is eliminated from the memory, right? Because whenever we are not using a system, we release the memory to save the resource. So, well, we will learn how we can do that, representing that kind of information in the sequence diagram as well. Then we also have a class diagram. Yep. So this is a class. This is a classes. Okay. So in the system we have a whole bunch of classes. Like here we have a student class, course, scheduling algorithm, registration, course offering, whole bunch of classes. Okay, class diagram, it has for every class it has 3 sections. First is the name on the top, and in the middle, guess what goes into the middle. So in a class we have members, we have operations, right? Of course, the name goes to the top, and in the middle it's the members. It's the same order. It's members in the middle, and the operations in this third part. Okay, operations. So here, professor name, and in the middle we put the members and members or attributes we call it. And in the third part we put all the operations there. We define the operations there. So what is operation? That's kind of like what we said, method of a class, like turn on the light, turn off the light. That's the operations method there. So here it's the same. So this is the example from the last sequence diagram. It's a registration form object. It calls the function from the registration manager, which means the registration manager has an operation, a method called 8course, and it requires the parameter of a student and the course the student wants to enroll. Okay, and like I said, this operations, it goes to the third section of a class. All right, and also the attributes. Right, the structure of the class is represented by its attributes. Attributes is important, and also the state of an object is defined by the different value of the attributes. And attributes may be found by examining class definitions, the problem requirements, and by applying domain knowledge. Okay, so what your design goes there. Okay, like if we design a class of the course offering, first we need to have the course number, right? The location and time. And what else should be here? Should we put instructors? Instructor.
Yeah.
Well, actually, well, If we think about another course, another class, course section, that's where you put the instructor there. But for a course, usually it's not associated with a specific professor, right? Because I teach this course this year, maybe next year some other professor will teach this course, right? So here I think number, location, time, it's okay. Yeah, I think it's okay. Oh, maybe a prerequisite, something like that. It goes here, prerequisite, right? Yep. So these are the classes. You have the course. We have name, number of credits. Yeah, that's another information. And we have an open 8 student. Those are those functions. Okay. And also we have for these classes, these are the classes, right? We need to define the relations among all these classes. So it's a pathway for communication between objects. The sequence and the collaboration diagrams are examined to determine what links between objects needs to exist to accomplish the behavior. Okay, if two objects need to talk to each other, means they want to do something together, collaborate, there must be a link between them. All right, and there are 3 types of relationships. Okay, I'm gonna talk about every one of the. Let's see. There's a whole lot of definition. Maybe we can dive into this example. And go back to that. What's that? Okay, 3 types is yeah, association, aggregation, and dependency. So maybe I go through this well, definitions a little bit. All right. So association basically means a bi-directional connection between the classes. And association is shown as a line connecting the related classes. And aggregation is the stronger form of relations, while the relationship is between a whole and its parts. And aggregation is shown as a line connecting the related class with a diamond next to the class representing the whole. Let me show you an example here. This is the aggregation. Course, from course to course offering. Alright, and we have diamond there. Why? Because it shows that course offering is actually a part of the course. Right. Let me see another example. For example, human, an object of human. Okay, human, and we have another object like hand. Human and hand, 2 objects. What do you think the relation between these 2 objects, 2 classes? A class of human and a class of hand.
So hand is a part.
Yes. Hand is a part of a human. Hand is a part of a human. So that's actually an aggregation. And where do we put this diamond? Okay, now it's clear. Hand is a part of a human. So hand project is part of human project. Or we can say a human object, human object, contains a hand object. Okay, like if we define a class, okay, class human members, eyes, maybe head, torso, hand, leg, something like that. Okay, so definitely that's a member of it. And if we define those two classes in a class diagram, we actually need to connect them with the aggregation relations, with this diamond on the part of human. So here we say human, and here we say hand. Okay. So the diamond mark should be put close to the hole, and the other end is connected to the part of that whole part. Okay, so that's aggregation. And those are general associations, like this registration form, registration manager. They are actually this bidirectional. It's bidirectional, so they are actually using each other or something like that. The dashed line is a dependency. Here. A dependency relation is a weaker form of relation showing a relationship between a client and a supplier when the client does not have semantic knowledge of the supplier. While a dependency is shown as a dashed line pointing from the client to its supplier. It's just using, okay, this registration manager is using the scheduling algorithm, but it's actually do not have a whole lot of information of the scheduling algorithm. It's just using that. Right? So it's a weaker relation. We can have a multiplicity and navigation. So multiplicity defines how many objects participate in the relations. Okay, multiplicity is the number of instances of one class relate to one instance of the other classes. Let's see here. See this? We have a number here from 0 to n, and this is 1. Okay, so this is from 0 to 4. This is 1. For professor, this means one professor. They're offering 0 to 4, actually up to 4 courses. Right? So that means when we have these relations here, usually the professors, and when these two classes are there, we have a limit there. So it's a 1 to n relation. Here we further define that n is up to 4. Okay, but if we use a star there from registration manager and the registration form, it's actually a 1 to n relation. Alright, so that means one registration manager that can handle n registration form. Okay, so it's not like 1 to 1. Alright. And here, let's think about course and course offering. It's still also 1 to n. Let's think about human to that hand. What it's 1 is n to n or 1 to n or something like that.
1 to 1 to 2.
Yeah. Well, usually it's 1 to 2. Yes. Yes. It's from 1 to 1 to 2. And registration manager to course is 1 to n. So we have those numbers here, and our course offering it's student. Well, it's 1 to 4. Actually, one student can take 4 courses, but one courses can hold up to maybe 3 to 10 students. Okay, that tells you this definition. Okay, for those elements, you can define them there or not. You can. It's an option. It's not like when you trying to draw a class diagram, you have to include all this numbers and things here. It's option actually, optional. That's a multiplicity. Multiplicity. And although association and aggregation are bidirectional by default, and it's often desirable to restrict navigation to one direction. Okay, so that means here, you see student to course offering. You see that part? There's no direction, right? That means bidirectional. But if you put the restriction on, for example here, from the registration manager to course, that's actually a one-directional relation. So that means course is actually not using anything in the registration manager, but the registration manager is using this course classes. Okay, so if you can indicate that direction. All right. And if navigation is restricted, an arrowhead is added to indicate the direction of the navigation. Alright, so you can actually use the navigation. Then inheritance, which is a very important concept in programming, in object-oriented programming. Okay, so it's a relation between a superclass and its subclasses. There are two ways to find inheritance versus generalization, one is specialization. So let's see, common attributes, operations, relations are shown at the highest applicable level of the hierarchy. Let's see if we define this inheritance here. Okay, it's here. So this actually, this connections, professor and student, they have a common superclass which is called registration user. Alright. So this is defined by this this line connect those two, and also a triangle, a big triangle there. Okay, don't say that's an arrowhead, this is an arrowhead, but this is triangle, and here course, this is a diamond, so this, let's call it triangle. It's a line and a triangle, and we put the triangle near the superclass or subclass. Superclass, yes. We put the triangle near the superclass, near the parent class, right? Yes. Okay, so we'll talk more about this next class, but now I want to talk about this project, our final project. Okay, here we define this project, so you can, right now you should be able to see the term project description and the plan, part 1. Yeah. Oh, I think I forgot to add the attachment to the description. I will do that soon.
You assigned the groups already?
Yes, and this is what I'm going to talk. So you can check your group from here, other group. So it's randomly assigned all of you into 4 groups. So it's not like I mix the face-to-face session and the hybrid session and the online session. So I want everyone to communicate with your group members through email or through the D2L, any communication, ways of communication. I mean, this is important part. While collaboration is an important part, communication is an important part of being a software engineer. So you should be able to get in touch with your group members as soon as possible. But what you do is go to this group and check this group and check your group members. So this is for both online student and hybrid session student. You are all mixed into groups, so trying to get connection with each other as soon as possible, because our first assignment of the group project, of the term project, is will be due after, I think, 10 days. Yeah, March 15th, yes. And it's a group project, so each group only needs to turn in 1 copy of that documentation. So in this term project, we're going to design some system. Okay, just we're going through the design documentation, trying to define the system. Okay, that's what we're going to do. Should have.
Did one person turn it in?
What's that?
One person turn in the assignment?
Yeah, because you will find it's actually a group assignment Dropbox. So only 1 copy will be turned in. So you will find, and everyone will see the comments, the feedback, and the score. Yeah. All right. So yeah, I think I forgot to attach the attachment there. So let me do that later. All right. So everyone try to connect with your group as soon as possible. Okay. All right. Thank you for coming today.